Yeah, hello everyone. Yeah, it's our pleasure to have Tobias here to have him to share about his work on quantum machine learning of large data set using randomized measurements. Yeah, I think it's Tobias, you can take over the floor and start your presentations. Thanks.
Awesome, great. Yeah, thank you so much for inviting me to give a seminar. So I'm very happy to be able to talk to you guys. And yeah, as some know, I did my PhD in Singapore, so I only left in 2020. So it's great to be able to give a talk again here. So this work basically involves quantum machine learning, and it's more of on the experimental side. So I'm a theorist, but for this one, since nowadays you have access to quantum computers very easily, even as a theorist, you can do kind of a bit of experimental work, but there's also some theory involved. So it's like a mix of both. So this work was done in collaboration with Chris Self and Minji Kim from Imperial College. Chris is now working for Quantinuum. They used to be Cambridge Quantum Computing. And this work was published this year, actually. Okay, so as you may know, when we do quantum machine learning, we somehow need to evaluate how good is your, well, let's say we do general quantum machine learning, be classical quantum. In the end, we want to somehow evaluate, is our machine learning algorithm good or is it not so good, right? And to evaluate now, we need to put it into practice and evaluate in something, in some kind of data set, and see, basically have it learn from some kind of data set, and then put it onto practice and by applying into a new unseen test data set and see how well it's able to learn and extrapolate that what it has learned to new data. And in classical machine, what people like to use, they had some basic test data sets they use to train their algorithms. And one of the older ones that people like to use, I think, since today is this called MNIST database of handwritten digits. So that's just basically just a list of images with digits from 0 to 9. And then basically the quantum computer has to learn from these images and basically predict them. And this involves like 60,000 examples of different images. This was, I think, it has been used for more than 20 years. So this is like one of the older data sets, but people still like to use to benchmark how good is my machine learning algorithm. So it's like one of the universal benchmarks that people like to use. And yeah, so it's a well-recognized test for classical machine learning. And basically, when I did this thing, I thought like, can we actually do this also with a quantum computer? So well, this is well known in classical machine learning, but maybe can also the quantum computer maybe learn from this data set, and then we can benchmark it against basically can see how well is our quantum machine learning algorithm performing, and use this kind of data as a benchmark. But one thing that immediately pops out, if you think about this image, this data set contains about 60 to 70,000 images. So if you now want to learn from it, we have to consider that our quantum computers are kind of slow. So the Sycamore chip from Google has about 5 kilohertz sampling rate. So in general, quantum computers are relatively slow, from at least compared to classic computers, which are in the gigahertz range. To give a comparison, 5 kilohertz was something we could already do in the 1940s with classic computers. So quantum computers in terms of speed are quite slow, and I guess they're also not expected to become much faster. So in terms of how fast quantum computers are running, we are kind of in the 1940s. And if you now want to learn like a large data set of these 60,000 images, we can do a very easy calculation. If we use a method called quantum kernel learning, just doing this will take, learning the full data set completely will take about 10 years of continuous quantum processing time. So as you can tell, 10 years, that's a bit much. So it seems we're not able to do this naively. So this goal of this work is to basically challenge this view, and I'm going to show you how we can get the most out of the quantum computers that we have right now in learning from such large data sets in actual experiment. As a spoiler, we won't do the MNIST, but we will do something smaller, but I will show you like how one could extrapolate easily with today's machine and even learn from these large data sets. Okay, maybe just a rough overview. I think most how we do quantum machine learning. In general, there's like two main paths to how people do nowadays quantum machine learning. On, let's say, on the more applied side, one is basically what people call variational quantum machine learning, where the idea is that you have a parameterized quantum circuit and you load your data into this parameterized quantum circuits, and also you have some kind of trainable parameters of the circuit. And then you optimize these parameters of the quantum circuit such that you kind of learn from the data. And the quantum circuit basically is then basically optimized in respect to some kind of data set, and then basically learns from that by optimizing these parameters. It will of the quantum circuit, it will learn to distinguish, let's say, images, let's say 100 digits. Yeah, this approach is very similar to how, let's say, how you would run a classical neural network. But the problem here is, of course, that you have to actually optimize parameters of a quantum circuit. So you have to do optimization on the quantum computer. So you have to compute gradients of the parameters on the quantum computer and implement them. And if you actually do this in experiment, you will notice that this is very time consuming and will take very, very long time to actually do it on a quantum computer. So for current machines, doing this for more than a few qubits is not really feasible at the moment. So since we want to do some experiments here, we opt for the second method, which is called quantum kernel learning. The idea here, this kind of approach will basically just involves preparing states and doing measurements. There's no optimization on the quantum computer itself. You do some optimization on a classic computer, but the quantum computer is optimization free. So meaning you just have to do state preparation and measurement, which is relatively fast. And this is more suited for the current approach that we have right now. Okay, so how does quantum kernel learning work? So let's say we have a set of classic data, let's say images. And the idea is that each image, we will now put onto the quantum computer. And the idea is that each image is like a bunch of pixels, and you can represent it as a vector. So each image will be a vector x, let's say. For each image, we have a vector x with, let's say, m entries. M is our feature vectors, the size of the feature. So let's say if you have m features, this would correspond to, let's say, the m pixels of our image. And each x1, 2, 3 would correspond to the, let's say, the value, the grayness value of each pixel. And then we take each image, so let's say the first image 1, and we put it onto a quantum computer by embedding it. So one way of embedding is you can basically put each feature vector, each value of grayness, as the amplitude of your quantum vector. So this is one way of embedding called amplitude embedding, which we're not going to use in our work, but this is some way you can do it. But there's many ways how to do embeddings. So basically, we bring now our classical data into the quantum world onto a quantum computer. So now we have quantum states. Each quantum state will correspond to one image. So for each image, we have one quantum state. And next, we measure the distance between each quantum state. So we have, like, for each images, we have a quantum state. And we then, as next step, we measure the distance between one quantum state to the other quantum state. For example, then this is called the kernel, which is a measure of distance. And there's many ways how to define measures of distance. One way people like to use is the fidelity. So you just take the overlap between one quantum state and the other quantum state. But then you can also define kernel in different manners. And the idea is that after getting all the distances, you may see some kind of pattern. Let's say images does correspond to 1. Maybe they are more close-ish clustered in one region of the quantum state because they're kind of similar-ish. And similarly, maybe the images in quantum state correspond to, let's say, this digit of 4. They will all be more closer, let's say. And if they are different images, different digits, they will be more separate. And you get now in the end, you get like a huge matrix that encodes all the distance between all images. So let's say if you have L images, then you have L square, kernel matrix of size L square. And you can feed this into classical machine learning algorithms, let's say something called a support vector machine, which then uses this kernel to learn. And it will then draw decision boundaries between the different images using this information you got from the kernel. And then basically will draw some decision boundary, and from that you can make predictions on new data. And this has been shown that there is a possible speedup you can have. So there's been one instance where we know there is a speedup using these techniques for a problem regarding the discrete log. So we know in principle there could be a speedup there, a quantum speedup. Okay, so this is the theory, but let's say if we now put this into practice, there are some challenges we have to basically address. First, we have to ask the question, how do we actually embed data with a lot of feature vectors? So let's say an image with lots of pixels into the quantum computer in a reasonable time. Because let's say nowadays our computers are kind of noisy, so we want to make this embedding as efficient as possible. Second question is, like, how do we measure the kernel? Because the kernel is like if you have a lot of data, we need to measure this huge all the distance between all possible images. So this will take a long time in general. So is there a way to speed up? And the third question is, how do we deal with noise in such a way that we don't lose too much time? And in our work, we basically address all these three problems and find some approaches how to deal with them. Okay, so the first question is encoding. So let's say we have an image, our digit, and we put it into our feature vector. How do we get as many features as possible into a short quantum circuit? And one idea that has been proposed is that you encode this as parameters of quantum circuit, of a parameters quantum circuit. So the idea is we have a quantum circuit which is composed of single qubit rotation and let's say some kind of entangling gates. Let's say like these C0 gates, and we repeat the structure d times. And the idea is that each entry, each pixel is encoded as into one single qubit rotation. And the idea is that we fix some kind of starting point, theta r, which can be some number that we fix. And then the feature vector is of, let's say, the first pixel is encoded as an offset to this parameter with some scaling factor c. So let's say the entry for the first pixel, we would put on the first single qubit rotation, theta 1, the parameter of the first single qubit, theta 1, its value would be the theta r1 plus c times x, the first basically pixel of the image. And the nice thing about this encoding is that we need as many parameters of the quantum circuit as there's entries in our feature vector. So let's say if we have m pixels, we need only m single qubit rotation to implement this image. So it scales linearly with the circuit depth. So with this, we have a very efficient way of encoding data in our quantum circuit. And then we want to measure the kernel. Yeah, and the kernel, we measure simply as the fidelity between two quantum states. So we encode, let's say, two different images as two different quantum states, and then we compute its the kernel as the overlap between the two quantum states. So we now kind of ask the question, like, what does this kernel look like, and is this kernel actually useful? And as a side note, this is a so-called hardware-efficient circuit. So these kind of circuits are known to be hard to sample from classically. So classically, you won't be able to simulate them efficiently for many qubits. Okay, one way what we're gonna shortly introduce is one way to evaluate our kernel. We use a concept called the quantum-efficient information metric. What the quantum-efficient information metric measures is that given a variation in our circuit parameters, theta, how does my quantum state change? How does my kernel change? So if I change my parameters by d theta, by how much does my overlap change? And the quantum-efficient measurement is a metric that describes this change, which is given by this by derivatives with respect to the quantum state. This is something you can actually also measure on a quantum computer. And this measure F, this matrix F, gives you a way how to evaluate how does a change in parameter that induces a change in the space of quantum states. So it's and this kind of metric is quite useful because what we found is that for this kind of quantum circuit, you have these single qubit rotations and some kind of entangling gates. We find that the kernel that you get can be approximated by the radial basis function kernel, which is kind of a Gaussian. And what you get is basically, I plotted below, we find this numerically quite well. So what the kernel can be approximately written as the exponential of the scaling factor c squared. And then you take the difference between different images and you multiply it with the quantum-efficient information matrix. And again, multiply with the vector of the two difference between the two parameters. So this is some kind of weighted overlap. And the kernel just follows this thing. This is a radial basis function, a well-known classical kernel. And we did also experiments on the quantum grid, and we can show that it pretty much follows this approximate equation quite well. So that means the kernel that we generate from these hardware efficient circuits has a classical approximation, meaning there is no quantum advantage, sadly. So we know these kernels actually won't be better than classical computer. But it's also quite surprising because naively, if you think about it, these circuits, quantum circuits, are known to be hard to simulate. So there's no way to simulate it on a classical computer. However, the kernel has actually a a classical approximation. So this was quite surprising for us. And actually, recent work even extended these results. It was been shown by a group of Jens Eiser that actually there's a large class of these kind of quantum encodings which have classical approximation. So it seems that most quantum kernels that you get using just bidirectional quantum circuits, there will be a classical approximation for that. So there will be no quantum advantage for that. So generally, it seems not clear how to make quantum kernels which are in some way better than classical kernels. So this is an open problem. Nonetheless, since this seems to be a general issue, we now stick with our encoding. Although we know there's no advantage, we still know it's like a well-defined classical kernel, approximately, and we can still run it in a very compact manner. And we leave this problem as for the future. The neat thing I want to just shortly show you too, that the confirmation metric helps you actually learn a lot about kernels in general. So what I show you next is very general. It does not apply to our kernel, but it applies to all kernels. Namely, whenever you have a kernel where you implement the image as a small shift. So let's say your xi is your image, the pixels of your image, and the theta is some fixed starting point you choose, and you encode your image as like a variation of the initial starting point plus the image with a small scaling factor. In this case, you can write the kernel very simply as in this form here. As 1 minus c squared, where xi, f is the coefficient measurement. You basically just convolute it with the feature vector. And so it actually has quite the simplistic form as a kind of a quadratic. And if you do you can actually now take do eigenvalue, find the eigenvalues of the coefficient metric, and the eigenvalues and eigenvectors of the coefficient metric tells a lot about how the kernel is behaving. For example, if you basically the eigenvalues tell you which directions in the parameter space lead to a strong change in the kernel, or which direction lead to a weak change in the kernel. So basically, the eigenvectors basically tell you in which direction the kernel will show a strong change, and which direction it will show a small change. So it basically kind of gives you a bias in the kernel. So it's like some kind of way to, and we know that these kind of approaches can help you to improve, for example, generalization. So this is a very useful thing you can use to study how is your kernel behaving and how well it will be able to learn from data. Okay, now the second challenge is how do we measure the quantum kernel actually in practice? So pretty much all experiments that I've seen so far, they use mostly something called the inversion test. Okay, so in the end, what the kernel is this matrix here, right? So in order to measure the kernel is a matrix which holds all the distances between all images. So let's say if L images, you need to measure on the order of L square different kernel entries. And how you do this is normally by either using something called inversion test or swap test. The idea is that you prepare the quantum state using some unitary. Let's say the quantum state corresponding to image I, and then you apply the inverse unitary corresponding to the image J, and then you measure. And from this, you can immediately extract the kernel. Alternatively, you can also use the swap test to measure the fidelity between the kernel. But the issue of both methods is, of course, that the number of measurements you need scales as L squared. So if you double the amount of measurements you have, then double the amount of your data set, you need 4 times the amount of measurements. So it scales quite badly. And especially if you have larger data sets, this will become a very large number and will not be feasible with the current clock speeds. So what we propose is to use a technique called randomized measurements or shell tomography to validate the kernel. So the standard approach that normally people use to basically measure something is first they decide an observable. Let's say I want to measure my kernel between 2 images, and then I make some measurements. So apply some POM and then make some measurements. So first you decide the observable, then you measure. In the shadow approach, we basically put this on the head. The idea is that you just make measurements that you kind of choose randomly. And after the measurements, you then decide what observables you want to measure. So it's like measure first, and then afterwards you think about what you actually wanted to observe. And the idea is that you make measurements in order to construct a classical representation of your state. And people call this the classical shadow. So you make measurements, and from the measurements, you construct a classical representation of your state that encodes the key information that you care about. And after you have this classical shadow, you can now use it to calculate observables. The key difference is now that once you have the shadow, you need only a shadow for each image individually, right? Because you can compute the shadow directly from the quantum state itself. So for each image, you would now compute the shadow. So if you have a data set, let's say of L images, you would now compute L shadows. And then you are basically done. You have your shadows, you have everything you need, all the information that there is, that you want to have. Meaning from these, meaning the number of measurements you need to perform only scales linear with the data set size, which is of course now better than the L square scaling that we had previously. And of course, in classical post-processing, let's say you want to actually construct the kernel, the classic cost will be still L square with the number of data set, but classical computers are relatively fast, so this is less of concern nowadays for us. Okay, so how do we do this in practice to when we want to compute the fidelity? We prepare our quantum state, let's say, corresponding to the image. Then we decide on a set of high-random singular rotations, and we measure on a computational basis after applying these unitaries. And then we repeat this for different sets of random unitaries, and we make measurements. And we do this for our all L images. And then from post-processing, there's a simple equation how you can reconstruct from the measurement outcomes. You can now compute the kernel. Of course, there's a price to pay, because in general, this requires exponentially many measurements with the number of qubits, because we need to construct like a representation of the quantum state, a classical representation, and in general, this will scale exponentially. So this is the price we pay. But as long as our system is small, let's say on the order of 10 qubits, we can show that actually already on the order of 10 to 100 data points, our method will be much faster. So this method works very well if the number of qubits is relatively small. We only, for even a modest number of number of images, there's an advantage of using this method. Okay, so for intermediate number of qubits, this method is faster. But now you can ask, let's say we go now to more qubits, let's say we want to scale up to hundreds of qubits, then obviously this method won't work anymore. But we know that shadow can be quite flexible, and we can simply use a different kernel, for example. So, for example, there's a kernel that's recently proposed by using this kind of reduced density matrix. And from this kernel, for example, you can show that this kernel requires only a polynomial number of the number of measurements you need to estimate this kernel. Using shared homomorphism will also scaling polynomial with the number of qubits. So simply by choosing different kernels, you can achieve better scalings if you want to. So there's a lot of room to play with these shared homomorphics. There's many ways you can find kernels with better scalings. Okay, but for now we have only access to lower number of qubits, so we stick with our fidelity kernel, and we basically use that one to proceed. Okay, the third challenge we have to deal with is error mitigation. So basically with the errors of the quantum computers. Since our quantum computers are kind of noisy, they will be prone to errors, and the result we get will not be the result that we actually would like to have. So the idea of error mitigation is that we try to fix the noise in our measurements, in our quantum states, by taking more measurements. So the idea is that what we measure is some kind of noisy distribution, which is away from the true solution. Then we apply some kind of measurements approaches. We measure in different ways to reconstruct what would the original result would have been if there was no noise at all. And from that, we can reconstruct, hopefully, the original true value of our observable. So there's results. We know that this only works for a limited amount for limited depth. So in general, error mitigation will scale exponentially with the number of the circuit depth. But in practice, it can work as long as the noise is not too severe and you don't have too deep circuits. There's many different methods people have used. For example, noise extrapolation, virtual distillation, or probabilistic error correction. All these techniques one can use, but the problem is, like, as again, we have the issue that we want to measure a very big kernel matrix. And what all these techniques in common, that you need to do some kind of lot of measurements in order to fix this. So in practice, because we only have a limited amount of money and time, we have to think of some error mitigation things that is a bit cheaper. So we try to think of a method how we can do error mitigation as cheap as possible, such that, like, it can even be applied to large data sets. So basically we try to find the simplest way to do error mitigation. And in fact, I will show you that we can do a way of error mitigation, which is kind of free of cost. We have to pay no price. Namely, we make a very simplistic model, like the most simplistic model you can think of. We assume depolarizing error. So we say that we have our pure quantum state representing our image, and with the chance of p, it is replaced with the chance of p. So it says here 1 minus p. This actually should be a p. So with the chance of p, it is replaced by the identity matrix. So that call it the maximally mixed states. Okay, and if you make the simplistic error model, we can basically show that now from the randomized measurements, we have access to the kernel. So the overlap between two different quantum states. And of course, we also have access to the overlap between the same quantum state with itself. So we know the trace of rho with itself. So trace of rho squared. So this is the purity. And we can easily show that the purity is directly related to this depolarization probability P. So once we know the purity, we know the depolarization probability. So we can now think of an easy way to do a error mitigation, where we basically mitigate the kernel by basically dividing out this depolarization probability, and assuming this model, we can find the correct value directly. So this is a neat thing. By using these randomized measurements, we actually wanted to measure the kernel between the images, but we actually got the purity and the depolarization probability for free on top. Although we actually didn't think about it, actually it was there for free. So that's a nice thing of shared homography. You can also extract features which you actually initially didn't think about. But once you have the data there, you can also measure other stuff and extract other stuff. And we also show that this method will scale a polynomial with the error. So this is something that works, in at least for modest errors. Okay, so with this, basically we found a way to freely correct errors, to cheaply correct errors without any additional measurement cost, directly from our measurements that we already have from our shadows. Okay, so we now have basically all three things that we want to achieve. We have some encoding. We know how to measure in a linear time, the dataset size, and we know how to do error mitigation in a cheap way. Okay, so now we apply this to supervised learning. So it is, we have our images that we want to learn from, these digits. We encode them into this circuit here, where each pixel will correspond to one single qubit rotation. We make our quantum states, and we have L images, and we measure them, each them. In the end, we have L shadows, and from that we compute our kernel. And the kernel is then fed into a support vector machine, which is a classical. Okay, so basically we measure our kernel, which comes from the quantum computer. And once we have the kernel, the quantum part is done, and we feed it into a classical algorithm. It's called support vector machine, which uses the kernel to learn. And it's basically doing that by using the kernel to construct a decision boundary that separates its different digits. So we'll basically say, given a new data set, new data, it will basically, using this kernel, will infer, is it a 0, is it a 1, is it a 2, by drawing decision boundaries, and basically saying it's more likely to be either a 0 or 1 or 2, given the kernel we already have from our training data set. Okay, and with this, and with this, basically, we applied this in practice. And what we did is, we did an experiment on the IBM quantum computer. And we took a data set which consists of 100 digits, 0 to 9. We didn't use the MNIST data set, but a different data set, because MNIST is still a bit large for what we have access to. So we used a different data set which contains about 1,800 images and about a feature vector of 64. And this we can encode in 8 qubits. And we basically now run this on the IBM quantum computer. So we just really, encoded all the 1,800 images and did our measurements, did our randomized measurements and constructed them. And in terms of runtime, it took us about 7 hours to run it in total computational time. And just as a rough estimate, we can also compute what would have taken it if, let's say, we do the version test or swap test. The number of measurements would have been on the order of 100 times larger, so it would be not really practical. And to our knowledge, like 1,000 images is the largest data set that has been measured. So I think there was an experiment by Google where they measured about 300 or 400 images a few years ago. So I think, and this took a much larger because they used the inversion test. So our method works quite fast and is able to learn quite large data sets on quantum computers. Okay, and the end result is shown in the bottom in the image. So what we plot is the accuracy for testing. So basically we have a training data set. So we have a set of images we classify as training data set from which we exclusively learn. And then we have another set, which we call the test data set, which is like new images that have not been seen during the learning, that we then basically check whether or not our algorithm has worked well or not. So we use then test data set to verify whether or not we be able to learn well. And we check what we plot here is the accuracy on the test data set after training. And what you see in the bottom is the training data size. So we varied like how much data we give into our algorithm to learn from. So how much training data it was given access to. And you can see like the more training data we give our algorithm, the better it gets. And we see eventually will saturate once the training data set becomes relatively large. And you can see now we plot now different results. So we did some theoretical studies where we used, in blue, we used as a baseline, we used a classical algorithm, we used a radial basis function kernel. And the orange curve is the exact simulation. So we used our exact quantum kernel to simulate. And the green curve is our is a simulation without any noise, only using short noise, but there's no experimental noise involved. And the red and the yellow curve are experimental results, where the yellow one is without error mitigation, and the red one is with error mitigation. And what we can see is that our experimental result in red and our simulation that includes no experimental noise, but only short noise, they match pretty much perfectly on top of each other. So meaning we can already, with our techniques, we can achieve the same result you would expect as what you expect using short noise. There's still some limits and like some difference to using the exact kernel, which would involve, of course, like having exact access to exact quantum kernel, which in principle would need to take you need to take an infinite number of shots. So there's still some difference to that, but we come relatively close given all the constraints that we have. So because we can show that we can learn even these quite large data sets, we can learn in very, very short time, in like only in 7 hours. Okay, we also did this next step. We also tried to do distributed quantum machine learning. Because I said, as always, the issue is that we have a limited amount of time in our lives and we want to make things as fast as possible. And one way is to parallelize, meaning we don't run everything on one quantum computer, but we parallelize our data on different quantum computers. So we have access to different quantum computers and we basically separate our training data into batches. And one batch is fed into quantum computer 1 and the second batch is fed into quantum computer 2 and so forth. So we have now different quantum computers that will now process one part of the data. And the nice thing is because after processing, we get the end results in form of these shadows, right? And once we have the shadows, we can compute the kernel also between different machines. So we can take the shadow for, let's say, one image from one computer, and we can easily directly compute the kernel that was from a shadow from a different quantum computer and just compute the kernel. So the shadow homomorphy approach, is very well suited to this parallelized approach. And of course, if you have G quantum computer, then we achieve a speed up by a factor of G in general. What we observe is that it works reasonably well. What we observed is, of course, the different quantum computers had different performances. So one quantum computer was better than the other. So this means that the results from the quantum computer which was worse kind of drag down the overall result. So it seems if one quantum computer has more errors, then this will drag down the overall result because you need to this will also affect the results from the other quantum computer because we compute the relative overlaps. But nonetheless, it showed that it works. So we can get some reasonable results using our machines and achieve, although it's a bit lower, we can achieve similar performances. And this is quite interesting. We would have to study in future, like how the different noise profiles of different quantum computers affect when you now take relative shadows from different quantum computers. How does it affect the overall end result? So this will be something very interesting. Maybe there's a way to fix this because we get a lot of information from the shadows. So maybe there's a way to extract or construct better noise profiles that somehow are able to fix the difference between different quantum computers and somehow fix the relative errors. Okay, so with this already, I finished the main results that I wanted to show to you. So I showed you that by using these randomized measurements, we can now go from L square scaling to a linear scaling in terms of dataset size. This method works very fast for 10 qubits. So we can show like it's much faster if you have like an intermediate number of qubits. In general, it's not scalable, but we know there's ways to improve this by using different kinds of kernels. We can actually scale this up method to any number of qubits and find efficient scaling. So there's approaches to improve that a lot. And also showed you how to efficiently encode data by using a linear circuit depth, and also how to do error mitigation for free. And just as a teaser or as a potential idea, what we can do with our techniques is that so far our image size was about we had 1,800 images that we learned from. Of course, if you now go to the endless data set, it takes a bit more because that has about 6,000 to 7,000 images and also has my pixels. But using a very basic calculation, we can show that even 20 times 10 28 pixels already fits in principle on 9 qubits. So you can show that you can find a complete representation that encodes all the information that is within the images. So you can basically, without information loss, you can encode all the pixels even on 9 qubits, because 9 qubits holds on the order of 2 to the power 9 different states. Sorry, not states, but so it's 2 to the power 10 different parameter directions. So by using 43 layers, you can actually encode this whole the pixels or the image completely without using any PCA or any reduction methods. And by using the same parameters as we used for our approach now, for a small data set site, it would take about 220 hours to run it completely, or 60,000 images using the shadows. And if you would like to use the inversion test, as I said earlier, you would need 10 years to do it. So it will be not possible. So this is something very much feasible. So if you have that much computational time available, with our technique, you could run the full endless data set and learn the whole set and see basically how it compares to other machine learning techniques. Okay, yeah, so these are main things to do is, of course, explore kernels with polynomial scaling. And also, actually, as I said earlier, like we actually, in order to be better, hopefully, we would need a quantum kernel which actually has advantage. And how to do this is not clear, since there's many kernels which have a classical representation. So this would require more work to think about how you actually construct a kernel which is possible to give you an advantage over classical routines. All right, so with this, I told you my story. So with this, I thank you much for your attention.
Yeah, thanks, Tobias, for the very concise talks. And like, I like the way that you dissect the quantum, like the problem of quantum machine into 3 different problems, like encodings, measurement, as well as the applications. And actually, we do have one speaker of tackling the kind of like efficiencies of the quantum kernel methods issues. Like they are using like random field features basically to kind of like approximate the fidelity quantum kernels. So I guess you might be interested on this one as well. So for the audience, like if you have any questions, you can raise your hand or type the question in the chat. I could moderate it. But in the meantime, while you are thinking about your questions, maybe I could ask some questions. So I kind of like the way that you use quantum feature information to the kind of like measures to tell you, okay, which directions is best to go, that might increase a little bit of that. in that direction, you can get a lot of improvements in your quantum kernels, right? In the problems. Yeah. So for the kernel that you consider is basically a fixed kernel, we know like typically we don't know what kernel that we use that is bad for a given problem, and typically we will parameterize the kernel. Like in this case, we will do a parameterize on the data embedding and then trying to find the parameters that optimize the kernel such that it's like suitable for a given problem, right?
Yes.
I'm wondering like whether you have a way to kind of incorporating this like quantum feature information to help us determine the best kernel to use, because like currently what we know from classical literatures and already applied it in quantum is by using the so-called like kernel target alignment, basically trying to find the best, like basically trying to find a like optimize it with respect to the like best kernel that you can construct, which constructed by using the training data, like +1 -1 dependent on right, and then trying to find an overlap and optimize these parameters. Yeah. So I'm wondering like whether there's a possibility of using this like feature information to optimize this kernel instead, and then whether it will give some improvements on, or maybe like improvement in the training procedures. Yeah.
Yeah, definitely. So as you say, like by choosing this fish information metric, you can basically give weights to different direction, right? So you can say like that one parameter direction is more important. Then you basically would need to choose the fish information metric such that like in that direction, let's say there's a stronger change in the kernel, or maybe there's directions which don't matter at all. So then you would have the fish information metric in that direction should be basically 0. Of course, like now I say you need to somehow engineer the fish information metric. So right now I'm not really sure how to engineer it. I mean, you could train it. I mean, you can just write a variational quantum algorithm that optimizes the Fisher information metric. But to be honest, that answer is not really satisfying. But I'm pretty sure there's some way of classical engineering it. For example, we know, for example, how to construct a Fisher information metric, which is isotropic, which has like it's just a diagonal, it's just the identity matrix, and all the off-diagonal entries are 0. So this will correspond to a radial basis function kernel without any weights.
Right.
So that gives like equal weights to all directions. So there would be some kind of the baseline, I would say. So that one we showed in another work recently. We showed what we call the natural parameterized quantum circuit. We give such a circuit which has like a Fisher information metric, which is the identity, like very simplistic. And we also used that here for experiments. So that one worked quite well. So we have some methods how to engineer it.
Right. Okay.
Yeah, but yeah, it's not very extended. So I think your method, I'm not also aware of the technique you described to optimize them. So maybe that could be applied here. Would be quite interesting to see.
Yeah, that could be one interesting direction to go. We have some questions from the audience. Sorry, maybe I missed something in the conclusion side. The randomized measurement scales linears means scale linear all the time using for training. Okay, so the question is basically asking about the scaling. Is it linear in terms of the time, or in terms of the like number of qubits? What resources that you refer to for the scaling?
The randomized scale linear in.
I think it's like you scale linear in terms of the number of measurement that you have.
So it scales linear in the number of states.
Number of circuits.
That you need to basically L. So L is the number of images in your data set. So let's say you have a data set and it contains, let's say, L images right here. In this case, there's 8 images. So the number of so the number of measurements you need to do will scale using randomized measurement will scale as L. So let's see, you would need on the order of L measurements.
Yeah, because
like if you do inversion test, you need to compute like all the different overlap, so it will scale as L squared, right? So which will be grows much faster with L. So it means basically in terms of number of in time, it scales linear in terms of the number of training images. Yes.
Yeah. So for this one, I think it's like you kind of, because like for this L2 measurements, like for the inversions, basically you are doing like L2 times like measurements between each of the overlaps, right? And then now for the randomized measurement, basically for each of the state you measure it and then do the L2 time measurement on the classical computer. But eventually you have to compute enough product against, right? Just have overload the classical quantum resource to the classical resource, if I'm understanding correctly.
Yes.
Um,
I hope
yeah.
There's a second question, I think, regarding pre-processing.
Yes.
For the results I showed you, let me think. So I think for this result I showed you here, we used some pre-processing because this was a circuit which was more limited. So this was actually this natural parameter quantum circuit with the quantification information method being identity. For this case, I think we used some PCA. I think we reduced to like 30 or 40 entries. So like the feature vector is 64, but we reduced, I think, to 30 or 40. But we also did a second circuit, which is, you use a different circuit. For that, we didn't do any PCA at all. So we coded really all 64 parameters into that circuit. So I didn't show this here, but it's in the paper. So we can do it even without PCA. We can encode enough. In the end, it's just a question of, let's say, how deep can you make your circuits, right? So the lower the noise level, the deeper you can make the circuits, the more data you can encode. Okay, I hope this answers this question. I think there was another question from Thomas on, when do you get exponential and polynomial scaling? That's a good point. Let me, yeah. Okay, so one kernel is this fidelity kernel, right? So you take the overlap between two quantum states. So this is a global observers, right? Because it involves the full quantum state. You need to measure the full overlap between one quantum state and the other quantum state. So this is what we call a global property because it involves all qubits in some way. And we know for these kind of observers, they will scale in general exponentially if you want to know the overlap between two different quantum states. So it's been recently proven there's no way to measure this in general in polynomial time, unless for special cases. So it has something to do with locality, like is it global or local? And for example, this kernel here with the polynomial scale, this is like what people call a reduced density matrix. So what people do is they take the full quantum state and then they look only like at the subspace, like a few qubits, let's say, and then compute the overlap between, let's say, these few qubits of one image with the few qubits of another image. And because this is kind of a local property, it involves only a few qubits, this can be computed in polynomial time. And for this kernel, I think they take the overlap between the few qubits, and then they do this for all qubits. They basically go through in like kind of a sliding fashion. And because this only involves like a fixed number of qubits, then this can be done in polynomial time. So it has to do about locality, basically. But you can also think of other kernels which don't involve overlaps, but involve some observers. This one you could also do efficiently, but we haven't considered that one. So there's a lot of things one can think of beyond these. How do you construct a kernel?
Right. Yeah. So this one thing that actually kind of come over here is that in order to have this to construct a kernel using the radius density metric, the degree of entanglement in the quantum state shouldn't be too large. Otherwise, like the radius density will be very close to mixed states, and then it's pretty hard.
You have always this problem that the kernel will, like, if it's too entangled, or if you have the problem that the kernel value will become exponentially small.
Oh, right. Yeah.
Usually in the bottom right, we plot like the distance of the kernel, like how far apart they are, and you can find that the kernel will become exponentially small. And this is what people call these barren plateaus.
Yeah.
The issue is that, of course, then if your kernel becomes exponentially small, you don't really know how to measure it anymore because it's too small. And then you need more and more measurements. And also for the shadows, you can't avoid this because also for the shadows, you can need exponential number of measurements. So you also have to be careful that your kernel doesn't become too small or your kernel state becomes too entangled. So there's many drawbacks one has to consider when constructing kernels.
Do you aware of the kernel bandwidth paper by Ruslan's Chandolin from JP Morgan? Basically, like they also they do this kind of the same things over here. Over here you have a content strip parameters data R, right? So in their paper, basically they just we didn't have this content strip parameter, they only have a scaling parameter C. And then who is basically trying to tune this C, and then trying to resolve the curse of dimensionalities of quantum like fidelity quantum kernel. Because from Robert Huang papers, we know that for fidelity quantum kernel, if you increase your qubit size, like your system size, basically like the kernels will be close to identities, and then you could not be able to generalize well, right? In that papers, basically they say that okay, if you add this like C parameters in, and then these C parameters could be between 0 to 1, and then tuning this parameter, you'll be able to change from non-generalization to be able to generalize. I'm wondering like how is that related to your case? Because for your case, I think you only consider small C in order to for you approximations.
Yeah, absolutely right. Yeah, exactly. The C factor you mentioned is the same C factor in our case. So this is the scaling factor. So this is something you can tune in general. So we tuned it a bit, but we found like if you keep it in some range, the performance doesn't change too much. The only issue if you make C too large, you get these Barron plateaus, right? Your kernel becomes just exponentially small, and as if C is very tiny, then there's no variance in the kernel. So
Right.
there's some intermediate value you have to choose so it works well.
So what kind of range that you consider for these C parameters, by the way?
Oh, I don't remember anymore. It will also depend on your scaling of your X, right?
Okay.
Because there's a state, so it depends on how you choose the X as well. So I think we normalized our X such that our images, such that like their variance is 1 or something like this. And then I think C was like 0.1, but I may be wrong. But it's
0.1? 0.1?
maybe, yeah.
Okay. Yeah, because yeah, considering their papers,
But I may
they
be wrong.
found parameter C is 0.1. Yeah, the best
Yeah,
C is
I think it was 0.1, yeah. So that range.
okay.
But yeah, it's you can see it easily. It's like you can just play around with the Z and then see how it performs.
Yeah, of course.
Yeah.
Yeah. Currently we don't have the question from audience, like due to time issue. Maybe I could ask the last question. So basically from classical kernel theory, right, we know like the kernel can be decomposed into its eigen decomposition form, like using Mercer decompositions. I'm not too sure if you are aware of this. Basically, you can written it right in terms of like a summation of like eigen values times the eigen functions.
Yeah.
And then the sum basically could be finite or infinite. And in this case, basically the eigenfunctions will tell you what is the kind of the basis functions of your models, and the eigenvalue will just tell you how much weight that you place on these eigenfunctions. And it seems to me that there's quite a lot of relevance to the quantum feature informations, and I'm kind of curious if is there any relations between these two, and then if then there's kind of, because like now you just link the feature informations, like basically link the information theoretic quantity to some quantity that people interested in kernel theory. Yeah. So it seems to me that there might be a link, because like at least the role of eigenvalues for the feature informations and kernels have kind of a similar behavior. So there might be a relation that we can draw. And then typically, like okay, so like the exact kernel eigenvalue actually is quite could be approximated as well, just as like information. If like for feature information, the eigenvalue and eigenfunction could be find much easier, then it could be beneficial to tell us something about K, because for the eigenvalue and eigenfunction, they use this quantity to study quite a lot of properties, of the kernels using statistical learning theory. Yeah. So I'm just like curious about whether there's some relation, but of course this would be kind of like a subjective.
Yeah, absolutely agree. I mean, you can very easily show this relationship, right? You show like how you can rate the kernel to the eigenvalues of the kernel efficient information metric.
Right.
So this is valid as long as C is relatively small. So I think if you're in this limit, I think you can immediately draw also a relationship to the eigenvalues of the kernel, right? Because it's just a kind of a very simplistic relationship. So I think you can really immediately draw like a relationship with the kernel and also the eigenvalues of the kernel efficient information metric.
Right. Okay. Cool.
So in this limit, I think the same, but I think if you go to large C, then maybe the relationship is not so clear anymore, because This means like you do take large variation in parameter space, and you can't describe it just using kind of local metric, because the quantum Fisher is a local property. But if the kernel like describes things which are far apart, then this is not so clear anymore how to describe this just using a local metric.
I see. Okay, got it. Okay, yeah. There's no more question from me and the audience. Maybe we can like stop here, and like thanks Tobias again for the interesting talk. And then I personally kind of learned quite a lot of it. At least like we can see a way to do a large scale quantum machine learning problems on current quantum computers. Yeah, thanks again for your time, and yeah, thanks again everyone who joined the seminar. Yeah, see you guys.
Yeah, thank you so much. Thank you.
Bye.
Yeah.